All right, moving on to section 13. Uh, Technically on 13.3, but part two of chapter 13. So here we're going to focus all on how to find derivatives of functions that have more than one variable. Um, Big rule is that you can only take the derivative with respect to one variable at a time, right? Any other variables that happen to be there, we treat like constants. So, as an example, let's say that we have a three variable function f of x, y, z equal to xy plus yz squared plus xz. All right, and let's say that we want to differentiate that. If I just say that, take the derivative, that actually doesn't really tell me much of anything, because there are three different first derivatives that I could take, right? One with respect to x, one with respect to y, one with respect to z. Um, so I could find any of those derivatives. The example that we have in the notes asks us to find f subscript x of x, y, and z. All right. And when you see this notation, this little subscript, that means that you're going to take the derivative with respect to x, meaning that y and z are going to be left as constants. So if I take the derivative of xy with respect to x, it's the same as if I take the derivative of 2x. It would just be 2, right? So derivative of xy would just be y. Now, if I go to the next term, remember we're differentiating with respect to x. There is no x in that term, meaning that this entire term is a constant, and the derivative of a constant is 0. And then lastly, we have xz. If I take the derivative of xz, that's the same, again, as taking the derivative of something like 8x, right? It would just be 8, the constant. So we get z, which means that this derivative would be equal to y plus z. And side note, there are a couple of different ways for the notation here. One is using this little subscript that tells you which variable you take the derivative with respect to, right? The other way is to use something kind of like dy dx. It would be this. So this is the partial derivative of f with respect to x. All right, and with that said, this that we just found is an example of a first partial derivative. And when we have functions that have two and three and more variables, right, the derivatives are all partial derivatives. So, side note, if we wanted to take the derivative with respect to y or with respect to z, we would have gotten something completely different. Right. So remember, look for what you're taking the derivative with respect to. Hold everything else constant. Let's do another example. Let's say that we want to find, or let's say that we know we have a function f defined as the natural log of x times sine of x squared y. If I want to find the derivative of that function, again, I would need to specify what variable am I differentiating with respect to. So in our notes, we want to actually find two different partial derivatives. So we want the partial derivative of f with respect to x. All right, to find that one, x is going to be a variable, y is going to act like a constant. So I see that I have something with x times something with x, which means to find the derivative using x as a variable, I have to do the product rule. So that's derivative of our first one. Derivative of natural log x is 1 over x times the second one plus the first one times the derivative of the second one. And for this, we're gonna need to use our chain rule because the inside of sine is not just x. So derivative of sine would be cosine, and then we multiply by the derivative of the inside. So remember, x is the variable, y is a constant. So I would just bring the 2 down, and this would be 2xy. So to write this a little more neatly, we could write sine of x squared y over x plus 2xy natural log of x cosine of x squared y. All right, and that is the derivative of f with respect to x. Now to find the partial derivative with respect to y, right? Keep in mind we're doing the same kind of idea, but now y is the variable and x is a constant. So the natural log of x would just be a constant, kind of like if it were just the natural log of 2, that's a constant. Um, so the only thing that actually matters here is this sine factor, which we know the derivative of this will be cosine of that times the derivative of the inside, right? Natural log of x we're not really going to do anything with because like I said, it's a constant. It's like if this whole thing were 3, right? 3 sine of stuff, right? So natural log cosine of x squared y multiplied by the derivative of x squared y. Keep in mind though, x is the constant, y is the variable. So this is like if I had 5 squared y, right? That would just be 25y. Derivative of that would just be 25, right? So if I differentiate x squared y with respect to y, that's just x squared. And that's the partial derivative of f with respect to y. Okay. And then we have one more example with a first partial derivative. Well, kind of, not really. All right, and this time the function is going to be written in a slightly different way. Slightly different way. So this time, instead of calling our function f of x, y, we're going to say z is equal to x e to the x squared y. And we want to find both first partial derivatives, right? Evaluated at a point. So if I start by finding dz dx, it's not really a d, partial z, partial x. That's a better way to say it. All right. Again, x is the variable, y is a constant. I notice that I have something involving x times something involving x, so I need to do product rule. Derivative of x is 1 times the second one plus the first one times derivative of this exponential. And remember how derivatives for exponential works. You gotta multiply by the derivative of your exponent. So derivative of x squared y would be 2xy. And that's multiplying just the original unchanged exponential, right? So it's just the thing times the derivative of its exponent. So if I were to clean that up a little bit, we would get e to the x squared y. I could even factor that out if I want. And that would leave behind 1 plus 2x squared y. Okay, so I found partial z with respect to x. Now, if I want to answer the question, okay, first off, notational thing. If I want to evaluate this partial derivative at a point, I can write that and then this vertical bar. You might remember that from doing integrals in Cal 1 and Cal 2. Right, this just means that we're evaluating the derivative at a point, specifically at 1 natural log 2. So the way this will work, anywhere that I see x, I'm going to plug 1 in. Anywhere that I see y, I'll plug natural log of 2. So e to the 1 squared times the natural log of 2 multiplied by 1 plus 2 times 1 squared times natural log of 2. Okay, so let's review a couple of things about logs and expos. Remember, natural log is the inverse of exponentiating with e as the base. What I mean by that is if I have e to the natural log of something, it's just the something. So e to the natural log of 2, literally just 2. Right? And this 1 doesn't really factor into anything because, well, 1 times anything is just itself. So that's e to the natural log of 2, also known as 2. Another thing to note is that when we simplify this, we get 2 times the natural log of 2. This is an answer. This is correct. This is exact. But for the sake of being able to match things on your homework, which you may have to do, you could write this in a couple of different ways, right? I want to remind you, though, that when you have a number times a natural log, you can always bring that number inside the natural log as an exponent. So 2 natural log of 2 is the same thing as the natural log of 2 squared, or the natural log of 4. Another thing is we could always distribute this 2, which would now make this 4 natural log 2. And using that same log property that I mentioned, we could write this as 2 plus the natural log of 2 to the 4, also known as 16. So this is another way that your answer could be written. Always helps to know that algebra. Okay, so the next thing we need to do is find our partial derivative with respect to y. So continuing this same example, we have partial z partial y. Okay, and again, this just means that y is going to serve as the variable, and anything else, like x, is going to be treated like a constant. So remembering that our original function z was x e to the x squared y. Yeah, this x is a constant. So we're basically just taking the derivative of a constant times e to the something, like 7e to the whatever, right? So to take this derivative, we just have to worry about that exponential part, meaning we take the derivative of the exponent, again, treating x like a constant and y like a variable. So this would mean that we multiply by y. Oh, whoops, that's not right. By the derivative of x squared y, right, which would just be x squared, right, the number that is in front of y. And then the rest of that derivative is just the exponential as it is, unchanged. If I want to clean this up a bit, I could write this as x cubed e to the x squared y. And to answer the question, we have to take this partial derivative we found and evaluate it. So vertical bar, we're evaluating at the point 1 natural log 2. And again, same thing. Anywhere I see x, I'm plugging in 1. Anywhere that I see y, I'm plugging in natural log of 2. So we get 1 cubed e to the 1 squared times the natural log of 2. Right? And again, 1 squared is 1 times the natural log of 2 is the natural log of 2. And remember what we said, e to the natural log of stuff is the stuff. So e to the natural log of 2, that's just 2. And multiplying by 1 will not change it. So now we have the derivative at that point. Okay, looking at the next example, one thing that you learned about in your earlier calculus classes is that first derivatives can tell us the slope of a tangent line, right? Basically, it gives us the slope of a graph, right? Now that we have more than one variable, these tangent lines can be in a couple of different directions. So if I take the partial derivative with respect to x, then essentially I'll be getting the slope of a tangent line that is parallel to the x-axis. And likewise, if I find the derivative, the first derivative or first partial derivative with respect to y, then I'm finding the slope of a tangent line that is parallel to the y-axis. Right, and to illustrate that, we can look at the next example. So we want to find the slope in the x direction and in the y direction of a surface, and the equation of that surface is given by z equals x squared over 2 minus y minus 1 squared plus 25/8. And we specifically want these tangent lines to be at the point 1/2, 1, 2. And then it says to sketch an interpretation, which I will do. All right, so first, if I want to find the slope of a tangent line or the slope of even the plane, right? Like if you look at it sideways, right? Basically the line, yeah, just think of it like a tangent line. So I'm going to start by finding the first partial derivative with respect to x. Okay, so x is the variable, everything else is a constant. So x squared over 2, derivative of that will be 2x over 2, also known as negative x. Y minus 1 squared does not involve x at all, so that has a derivative of 0. 25/8 does not involve x at all, so its derivative will be 0. Which means that the partial derivative of z with respect to x is negative x. And if I evaluate this at the point that we were given, and it would work kind of like how we've seen it in the other examples, right? Anywhere that there's an x, I substitute 1/2. Anywhere that there's a y, 1. Anywhere that there's a z, 2. In this case, so there's only the x, so negative 1/2 would be the slope in the x direction for that surface. And to think about what that might look like. So let's say we have our z-axis here, we've got our y-axis here, got our x-axis here. Okay. The graph for this surface is going to be basically like a little paraboloid shape. Like your mom throws a bed sheet over you on Halloween and tells you to go trick-or-treating as a ghost. Spooky. Right. But anyway, essentially, if I look at this point, I know that it's going to be a point that's on this surface. just to make it look kind of 3D. Okay. Okay. So if I locate this coordinate that we were given, 1/2 in the x direction, 1 in the y direction, 2 in the z direction, I might be, say, right here, right? What we just calculated, -1/2, would be the slope of the tangent line that's parallel, or that touches at this point and is parallel to the x-axis. So essentially, it's just something like, I'm trying to make this parallel. There we go. That's still not really parallel. I'm trying. Yeah, so parallel, boom. Right, so notice it's not actually cutting through the surface. It's just touching the surface at this one point and then kind of passing really close by the rest of it, right? It's just hard to see that with a three-dimensional drawing. And likewise, when we go through to calculate the partial derivative with respect to y, we'll get the slope of a tangent line that's parallel to the y-axis. Right, so that would look something like, well, actually, let's calculate the derivative first. So partial z with respect to y. Remember, that means y is the variable and anything else is a constant. So that first term does not involve y at all. Derivative would be 0. Here we would use our chain rule, bring the 2 down, take 1 away from the power. So we get -y minus 1 and multiply by the derivative of y minus 1 with respect to y, which would just be 1. And then that last term, 25/8, does not involve y at all. So derivative of that would be 0. So if I were to take this partial derivative and evaluate it at the point that we were given, same old song and dance. Anywhere there's an x, it's 1/2. Anywhere there's a y, it's 1. Anywhere there's a z, it's 2. So with this one, we get -1 minus 1, also known as 0, which means that, that's why I wanted to wait on that one, which means that when I draw the line that is tangent to the surface at only this point and parallel to the y-axis, it's going to represent as a horizontal line in the YZ plane. Likewise, if we were to take likewise, if we were to take the XZ plane and look at this line, it would be a line that has a slope of -1/2. That might look counterintuitive because it looks like the line is going up, but remember, coming out of the page, X is getting larger, right? So as X is getting larger, the Z value is getting more negative, right? So that would be a negative slope. A little topsy-turvy, flippity-floppity, but there we go. All right, and that's that example. So now you kind of have an idea of what our first partial derivative can do. Here's another one. So um, this is the last first partial derivative we'll look at. All right, but let's say that we know that the area of a parallelogram is given by A times B times sine of theta, right? And imagine that this is our parallelogram, right? And we have, that is not even close to parallel. What am I doing? There we go. Better. Okay, so let's say that this is our side A, this is our side B, and theta is the angle that's between those two sides, right? The first part of this example, which I should label as a separate example, right, asks us to find the rate of change of A, the area, with respect to A, the side length, right? at a specific set of A, B, and theta. So it really wants us to find dA or partial A with respect to side length A, little a, specifically at the point where A is 10, B is 20, and theta is pi over 6. Right, so 10, 20, pi over 6. So at that point, I need to start by figuring out the derivative, a partial derivative of the area with respect to side A. So little a is a variable, everything else is a constant. So when I look at this, I see a variable times a number. It's like 2a or 7a or 3.14a, right? If I take its derivative, that would just end up being the constant. In other words, b sine theta evaluated at this point, which I can still technically write here, since the partial derivative is not the same as the partial derivative at one point. So anywhere that I see A, side length A, I would plug in 10. Anywhere that I see B, 20. Anywhere that I see theta, pi over 6. So I end up with 20 times sine of pi over 6. And because we are all unit circle warriors, we know that sine pi over 6 is 1/2, which means that the area of that parallelogram is 10. Now, for the second part, we want to know the rate of change of the area with respect to theta at the exact same set of values. So same parallelogram, what is the rate of change of the area with respect to this angle? So that's asking us to find partial A with respect to theta. And we want to evaluate at the same point, 10, 20, pi over 6. So this time we're going to have a different derivative, right? Because now theta is the variable and everything else is a constant. So now A and B are constants. So A times B is a constant. So it's like I'm taking the derivative of 872 sine theta, right? That would just be 872 cosine theta, right? But instead of 872, it's just AB. So AB cosine of theta. And again, we're evaluating at the same coordinate, 10, 20, pi over 6. If I make the substitutions, A is 10, B is 20, and cosine of pi over 6. So 10 times 20 is going to be 2 followed by 2 zeros, so 200. Cosine of pi over 6, we know again because we are unit circle warriors, we know that that's square root of 3 over 2. So this is the same thing as saying the square root of 3 multiplied by 200 divided by 2. In other words, 100 square root of 3. So as that angle increases, we can see that the area of that parallelogram is changing way faster than if we're just stretching this side length and keeping everything else constant. Gonna put it in perspective. All right, now that we're done with those first derivatives, let's talk about second derivatives. So I mentioned that when we take the derivative, we can only take the derivative with respect to one variable at a time. Okay. If I decide to do higher order derivatives, that same logic follows. So I could have partial derivatives with respect to the same variable twice, which means that you differentiate with respect to that variable and then you do it again with respect to that same variable. That's one way. But you can actually have what we call mixed partials, where you take the derivative with respect to one variable, and then for the second part, you take the derivative with respect to a different variable. And that's what we'll look at in this first example with second derivatives. Maybe. Yes, here it is. It's like, where did it go? So for this one, our function, we have f of xy equal to 3xy squared minus 2y plus 5x squared y squared. All right, and it wants us to start by finding this, right? And we want to use the result to find this. Okay, and here I kind of decided to use both notations so that you can see how they work, right? So both of these are different ways to write a second derivative, first with respect to x, then with respect to y, right? So the order that I write them is in that order. I'll talk more about order in the next example, but for this one, I'm going to start by taking the derivative with respect to x first. So kind of going to do some work on the side here. Start off by taking partial f with respect to x. I get 3y squared. Second term would be 0. Third term, we would get 10xy squared. Okay. Now, if I want to find the second derivative with respect to x, then y, right? I would take the result that I got from this intermediate step here, and I would take its derivative with respect to y. So derivative of this term would just be 6y. For this one, the x would be a constant. So the derivative of our second term would be 20xy. And this would be the first part. That's the second derivative, first with respect to x, then with respect to y. If you want to have a little fun, try doing it in the opposite order and see what you get. All right, so to answer the second part, we want to essentially just evaluate this derivative that we found. At the coordinate -1, 2. Right, and just a side note, you could also label this that we got here as f with a subscript xy. And if you really want to be proper, write what the independent variables are. So, just so you know, these notations are all interchangeable. And when we get to even higher order derivatives, one might be more favorable than the other. So anyway, wherever I see x, I'm going to plug -1. Wherever I see y, I'm going to plug 2. So going to our second derivative, we get 6 times y, so 6 times 2, plus 20 times x, that's -1, times y, that's 2. So I get 12 minus 40, which gives me -28. And that's the second part. Okay, so I mentioned I would talk about order. If, if both, I say both when I talk about two variable functions, if both partial derivatives are continuous, then the order actually doesn't matter. So if you had a little fun, like I said earlier, and tried to do this the opposite way, you should have actually ended up with the exact same answer. Right now, if you do them different orders, the algebra might be a little different, but the answers that you get are going to be mathematically equivalent as long as that condition is met, right? As long as the partial derivatives in question are continuous. All right, so in this next example, it asks us to actually show that that's true for third partial derivatives. So to begin, we have our function of three variables, f of x, y, z, all right, equal to y times e to the x plus x times the natural log of z. So with this one, we want to show that f of xzz is the same thing as fzxz, which is the same thing as fzzx. So this is just asking us to take third partial derivatives in different orders and show that they end up being the same. So for the first one, right, for fxzz, we start off by finding the derivative with respect to x first, right, which we also, for notational purposes, could write as fx. You don't need to do the fancy squiggly d's if you don't want to, right? And with that one, remember x is your variable and everything else is constant. So this is a number times e to the x. Derivative of that would be the number times e to the x, right? Derivative of x is 1, so that doesn't change. For the next one, the second term, we have x times the natural log of a number. Okay, so natural log of a number, that's just a constant. So that's a number times x, which would just be a number. So this will be our first partial derivative. Now, if I were to take the result of that and then take its derivative with respect to z, okay, remember we're starting from where we left off. The first term has nothing at all to do with z, so its derivative is going to be 0. Second term is just the natural log of z. We know that the derivative of that is 1 over z. And to get the final part of that, right, our third derivative, we're going to take the result and take its derivative with respect to z. So at this point, we remember that 1 over z is the same thing as z to the minus 1, and that we can do power rule with that, which will give us negative z to the minus 2. Remember, a negative exponent means that you could write that in the denominator, and this would be the third partial derivative using that ordering. Now to do the other two, fzxz, we'll start off with fz, first derivative with respect to z. That term, the very first term, has nothing to do with z, so its derivative is 0. The second term, we have a number times the natural log of z. So the derivative would be that number times 1 over z, which I could also write as x over z. Now if I take the second derivative, the next variable will be x. So I have x divided by a number. Derivative of that would just be 1 over the number. And then when I go for the third partial derivative, okay, we kind of do that same thing that we did in the last one. We remember 1 over z is the same thing as z to the minus 1. So we end up getting negative z to the minus 2, also known as negative 1 over z squared. So we got the same thing, even though that was a different order. All right, and this won't be complete until I've shown all three orders. So next one we have FZZX. Start off with FZ. We already know what that was because we did that. Okay, now you just have a number, a constant, times 1 over z. So to take that second derivative, FZZ, that would end up giving me negative x over z squared, right? Negative xz to the minus 2. Bring the z to the minus 2 to the bottom. And then to get the last one, we differentiate this with respect to x. So we have basically negative x over a number. Derivative of that would be negative 1 over that same number, which matches the other two. Pretty cool. Okay, and with that, we're going to start looking into the chain rule, which I'm going to have as a separate video so that you get an opportunity to stretch and drink some water, maybe get some caffeine or something. And happy mathing.